But like people's names, she knows how you're supposed to pronounce. She doesn't know how it's supposed to be pronounced. Nobody's told me.
All right. Sorry that took me a second to get the presentation all ready there. I was trying to get ArcGIS working before class. It took me 20 or 30 minutes. The license manager went down. I guess it was just last night because, Michael, you were saying ArcGIS was working fine yesterday. But I got a letter from several of the students that it wasn't working. And of course, none of them are here. So maybe they thought I couldn't fix it. Yeah.
I mean, that is a fair assessment, but I feel like they should have had more faith in it.
Yeah.
Or maybe it was spring breakitis. That's a serious disease going around this week.
I also heard that the IVN wasn't working.
And yet.
But Heather, I guess, got on that and got it all fixed up. So thanks, Heather. So that was the early class. So there's a remote sensing class, and lots of the undergraduates that are in this course are in that. No, the ones that Addie's were undergraduate. All right, so welcome back to me. Sorry that missed last week. I did have to assign interim grades over the break. So some of you may have noticed. So don't take a whole lot of stock in your interim grade. This is how I did the interim grade because I didn't have a lot of information to go with. And this is how you should interpret it, okay? So if you got an A on your interim grade, it means that you turned in all the labs and they all look good, okay? If you got a B, I was missing a lab. And if you got a C, then I was missing more than one lab. I think there were only 3 or 4 labs for this class that were due by the class. So don't worry if you got to see. What it means is there's probably a communication error, like you're sending your labs to the wrong place, or because I do get a lot of labs, I'm searching for your name. So maybe if you're not sending them using your name or something. But if you did get a C, please send an email to my regular email, george.raber@usm.edu. And if you say, hey, you should have gotten all my labs, but you didn't, then we can go back and look through that. So I'm saying this to the video because none of the Hattiesburg undergraduates are here. It looks like plenty of the Coast undergraduates are there. So if you Hattiesburg people watching this video later see that, or you down on the Coast see that, yeah, please communicate with me. Also, I'm going to, unfortunately this semester my courses aren't on the same day. I have a Tuesday class and a Thursday class. I'm going to teach my Tuesday class from the Coast the next time I teach it, so in 2 weeks. I'll get there a little bit early, like about an hour before class. If you want to talk to me in person, that's one time. I will in the maybe even that same Thursday, although probably it'll be the week after. So like that, I guess that'll be 3 Thursdays from now. I'll come teach this class from down there.
That's the day we have the test.
Oh, that's the day we have the test. So that wouldn't be as good of a day. So maybe anyway, I'll decide that. I just thought of mentioning that, so I'll decide that. But I always come down at least once in the semester and teach from the other direction. And usually I do with both classes the same day, but this semester they changed my course schedule. All right, so that's that. And again, your interim grade doesn't get recorded anywhere. It's actually for the purpose of being able to communicate some sort of feedback to the student. So again, don't worry if you got that grade, but make sure that you make a communication with me if you got a C, meaning that I don't have all your labs. I won't even count them as late if we figure out why that's happening. Did you have a question? No, just stretching. All right. Sorry. Download. this. So today we're gonna cover. It's basically a small bit of the last chapter. I think it was chapter 7 on area analysis. But then most of it is going to be chapter 8. And again, we're separating quite significantly from the book at this point. I mean, although we're covering basically the same topics, we're not covering them as deep as the book does. You can use the book to get some background information, but we're going to cover basically spatial statistics with emphasis on local spatial statistics today and regression, which are the topics of chapter 8. All right, I do have again, sorry, I don't have it ready right at class, but we'll get to that in a second here. I'm gonna open up ArcGIS real quick, so I have that open. Oh, I'm getting that error. If any of y'all do get an error on the coast, you might be getting this error because, let me do that for a second.
Are we starting this lesson from scratch or are we building this?
We're going to be using a lot of the same data, but it's different, different in nature. I think I'm just going to leave it on this screen. We can all see that because that way I see exactly what you're seeing, and I can move around and show things that'll be on the video. Because if it's on the other one, you said that the pointer doesn't show up, right?
Not very well.
Yeah, maybe I'll just leave it that. And that. Okay, what I was trying to say is if you're seeing this error when you try to open up ArcGIS, which I think you're still seeing on the coast, and I solved this here, every year we have to re-up our licenses. And so that needs to be done on the coast. And it would have needed to be done here, except for we had another error where ArcGIS wasn't even working. But you can just bypass this error. This isn't an error that says you can't use ArcGIS, it's just a warning, really. So if you just say, okay, ArcGIS will start right up, you'll be able to mess with it. And we're going to be utilizing, this spatial statistics. We're going to be utilizing the spatial statistics tools like we did before. See the data that we. By the way, getting off track a little bit. So this is some of the data that we collected while I was in Africa. So we were in a boat along a river. So the river channel's over here, and we flew these little UAVs out into the marsh. This is a false color NDVI, or sorry, just false color near infrared image. So the red stuff, the more intense red, actually the higher, the greener the vegetation, the more vibrant the vegetation is. And I just pulled this one out at random, but on plenty of these things, you can see evidence of animals moving around, although this one doesn't look as vibrant. But you can zoom in, you get pretty highly detailed imagery. This is papyrus. Papyrus actually has these they almost look kind of like large dandelions where the dandelions are blown. Because these spikes, that's what these balls are. And there's lots of different types of vegetation. So the purpose of the trip was to collect ground control for other less detailed imagery. All right. Let me see here. No, how come I can't? Oops, new, like that. There we go. No, I'm just going to add some data so that we can process it, or maybe we'll just wait till the lab if I can't get it really quick. Let's see. I'll get to the data when we take the break. Can't find my data from last week. So this has a lot of text here, but I know that at least for the GIT undergraduate, there is a statistics course that's required. It's over in, I think you have an option of taking sociology or psychology or something. Psychology. Did you take that as an undergraduate? I know you were a GIS. I mean, you did take it. From the coast, has anybody taken that course yet? Looks like one or two of you are starting to raise your hands. Three, a couple of you have taken that course. All right, so you definitely would get that course. You definitely get some of the information that you would that we'll talk about today. Okay, so we're going to talk about applying regression analysis to spatial data. Okay, so basically, the background here is that when we create a regression model, we are interested in coming up with factors that will mathematically describe a phenomenon. Okay, so the example here is we might use education level, income level, alcohol or drug use, proximity to an urban environment in order to describe a pattern in crime. So those would be considered the explanatory variables, and we'd be trying to predict crime. That's only one example. Whether or not you're interested in anything that you're interested in, you can use this concept of regression. Okay? So analyze those variables, and there are lots of different things that you can look at inside the mathematical model that it attempts to do. So why should we use regression? Well, there are a few different reasons. I didn't spell regression right on the slide, sorry about that. One is to find out how strong, thank you. How strong the relationship is. So in that earlier example with the different variables that were used to describe crime, okay? So one of the outputs for a regression model will be a correlation, and it'll tell you how correlated each of your individual variables are and how strong the total explained amount of variance will be. And so you can see, or you can make a decision on whether or not your explanatory variables are building an appropriate overall model for your prediction. Okay. So you can explore correlations. Are these things connected to this item? Is crime, so you're asking the question, is crime related to distance from urban centers, poverty, and that sort of thing? Are they related? Is there a correlation? Doesn't necessarily, statisticians will tell you, it doesn't necessarily mean that poverty causes crime if they're related, or if they co-vary, if they're correlated. It doesn't necessarily mean that, but it does mean that they are, that they have very similar patterns. When one goes up, the other goes up, or they can still be highly related in a case where when one variable goes up, another variable goes down. So like life expectancy might increase as the number of years that you participated in some crazy activity decreased. All right. Another reason that you might want to use regression is to predict unknown values. So, and for spatial patterns, this happens less often, but in geography, we apply this less often, but we might want to find out what a new variable is at another location that we don't know that location for. Where this does get applied a lot actually in geography is in remote sensing. So let's say we had a data set and we went out into the field, like the example I just showed, we went out into the field and we measured the health of some sort of plant in a bunch of different areas. But we measured that in the field. And then we could build a mathematical model to see if the measurement that we took for plant health, let's just say it was biomass. So how much biomass do we get in this 1 by 1 meter square? How much biomass do we get in another 1 by 1 meter square? How much biomass do we get in another one? We had like 30 or 40 observations of plant health. And we were somehow able to correlate those measurements, or to create a mathematical regression model, those measurements were able to create a relationship between the brightness values that we saw in an image like the one I just showed you and the plant health. Then it would be possible to predict the plant health for the entire region in which we had remote sensing data for. So that's one reason why we might use regression in geography. All right, and then understanding key factors is related to exploring correlations. Why are test scores higher in certain parts of the country? One way to do this is when we come up with a mathematical model that relates test scores to things like poverty, or test scores to income level, or parent income level, something like that. We come up with a model that tries to describe test scores, and we find out which ones are correlated. Sometimes it's very useful to look at those areas where the pattern doesn't necessarily hold true. Okay, why are test scores higher in certain parts of the country? So we've got our pattern, and then the areas that deviate significantly from the pattern can tell us. All right, in this course, we're not going to be directly creating a regression equation, and we're not going to do that intense math, but we're going to allow ArcGIS to do that. The equation, this equation here, is the general form of a basic or ordinary linear least squares regression model. It's just trying to get to fit a linear relationship between certain variables. So we've got our dependent variable. This is the variable that we're trying to explain. We've got our coefficients, which we multiply to each of the explanatory variables. So we feed into the equation the dependent variable and the explanatory variables, and ArcGIS, or whatever program we're using, will return the coefficients, and also give us an idea of how much random error, the residual term, for each of the models. We'll see this when we run it in ArcGIS. So if we were trying to explain residential burglary, that was our dependent variable, then our X variables, our explanatory variables, might be income, vandalism incidents, the number of households, and our hypothesis would be that burglary is a function of income, vandalism, and just the number of housing units. More housing units, more opportunity for burglary.
Let's see what this one is. Autocorrelation, that helps filter out autocorrelation.
No, the residual is the difference. So here's the residuals are the difference between the actual values and the observed values. I should have included a slide here. In fact, I did later. Okay, so this is a very simple relationship between unemployment rate and gross domestic product. So gross domestic product is the sum of all the output of the economy. So It's a very large aggregate measure of the health of the economy. Unemployment rate, incidentally, is also a large indicator of the economy. In fact, they are fairly related. In other words, as unemployment rate decreases, it looks like GDP. So this is the change, the quarterly change in the. So as the unemployment rate changes positively, then the quarterly change in the GDP also changes negatively. Negative relationship. So the residuals are the differences between all of these options. So this is the overall general pattern. Okay? It's the without explaining the math, it is the line that best fits all of these individual points. Does that make sense? So that's the line that best fits all of these individual points. And the residual is the difference between here and the line. So this is the actual value, and this is the predicted value at that x. Residual values there. So in our case, residential burglaries is the dependent variable. Explanatory variables are those other variables that we included that we're trying to relate to our dependent variable. The coefficients give us an indication of the strength and the type of the relationship. In other words, if these values are highly negative or highly positive, then they influence the shape of this line a lot. This line right here. Oops. All right, and then the residuals are the difference between the line and the observed values. So ordinary least squares regression is kind of like the starting point. ArcGIS allows you to run ordinary least squares regression, and it works by taking all of the individual points, and you tell which attributes you want to be your dependent variables, and your dependent variable, and which attributes you want to be your independent variables. And then it will create a map showing the outputs there. And it'll also generate a report showing you how strongly those are related. So many of you, if you've taken a course in statistics before, you've gotten a much more comprehensive explanation of what I've just talked to you about. We're just going to do it in ArcGIS. All right, and also, we're going to observe that technically regression is not spatial in nature. We can use individual points as inputs to regression, but we can apply data that's not spatial. There's nothing spatial about regression. So there's several ways to include spatial components. One of them is to include a geographically derived variable. Now we've practiced doing a spatial join and finding the distance to another object. So you could say, okay, I could throw in and make one of my explanatory variables the distance to the city. So there's a city somewhere in my data. Maybe one of the things that is predicting, in this case, 911 incidents, might be the distance to the city. So how far away we are from the city could influence that. Let's think of another example. One, like I still have this research trip on my mind, but you notice this almost all the way throughout the world. When you're on the water, right next to the area where the water is, what do we call that? The area right next to a river? A bank, the riparian zone sometimes. The vegetation is very much more intense at that location. Sometimes the trees are taller if they're not trees. Even if it's a monoculture, it's the same type of vegetation. The vegetation right by the river channel at the bank, the riparian area, gets more nutrients, it gets more water, and so those plants are taller. So if we're trying to explain the amount of vegetation in a particular area, we might say distance from the river channel as one of our explanatory variables, and we're trying to predict vegetation health. as an output predictor. That's a biophysical example. There could be lots of different applications for this, but one way to include a geographic component in regression is to include some geographically derived variable. Now, if you include lots of those, you run a risk of breaking one of the components of regression, which is that you don't want to have all of your variables be autocorrelated.
You could also do distance from shore, water depth. Distance from shore,
water depth, salinity. Those are also not technically spatial, but
those would still be good for regression.
they're still attribute based. I mean, they're spatial in that they exist at a particular location, but they're still based on an observation. All right, another way to include spatial analysis in your regression analysis is to analyze the pattern of the residuals on the map. We'll talk about analyzing patterns later. And analyzing patterns. I've got a cough or something, but we'll talk about analyzing patterns later. But we could take a map and say, okay, well, we created a regression equation. These are the areas that are significantly above the model, and these blue areas are the areas significantly below the model. What's kind of interesting that there seems to be a spatial pattern associated with areas that are above and below the model. We can try to explain that a little bit further, or we can analyze this map as a pattern later. Which we'll talk about later. Another way to include a spatial component in regression is to do what's called a geographically weighted regression. And ArcGIS will do this. And with geographically weighted regression, what happens is that a regression equation, instead of being calculated for the entire mapped area at the same time, an equation for each feature is calculated only using the nearby features rather than all the features in the data set. Okay, so basically the regression equation changes over space. These kind of say the same thing. This is from the ArcGIS help. This is more similar to what the book says. But you do have the ability to set how large an area you want to be included in the geographically weighted regression. That's what these different parameters are for. We'll practice this as part of the lab. Now, a warning here that at times, ordinary least squares regression may actually produce a better model than geographically weighted regression. Just because it's spatial doesn't necessarily mean that it's better. That's a reason that you'd want to do this. One of those reasons might be that you see a pattern like this in your residuals. You see, so there's a different pattern happening here than there is happening here. All right, now a lot of times the analyzing of these geographic patterns is referred to as spatial statistics. We actually have an entire course, it's a 700 level course, so it's not a course the undergraduates take. We have an entire course on this subject matter, we did talk a lot about this aspect this week. This is what we want to talk about this week: spatial statistics, quantifying geographic patterns. And this goes back to what we talked about several times: spatial autocorrelation. And almost all of these metrics that we're going to calculate today, well, all of them, produce or seek to explain spatial autocorrelation by boiling it down to a number or a series of numbers. This is an example output from ArcGIS, but it shows you this model of, this is really, really small. Maybe I should blow this one up. See if that looks better. as a full screen here. Not much better. Yeah, I can zoom in. Escape. Whole thing, or I can just make it bigger. There we go. Okay, so they work on a scale where a negative value means that your data is clustered. A value around 0 means it's random, and a value closer, a positive value means that your data is dispersed. And we're looking at a particular attribute. So we might be looking at poverty, or we might be looking at vegetation type. We might be looking at any variable that we can think of in lots of different fields. So they all exist on this scale, and we can do this looking at the overall spatial structure, or what they refer to as a global value, and then individual values. We'll look at it here in a second. So we've got some global measures and local measures. An example of global measure would be a single value that applies to the entire data set. So single value, but if it's highly negative, it's clustered. If it's highly positive, it's dispersed. That would be useful for evaluating, saying, okay, in this case, is illiteracy clustered in China? Does it happen in certain areas? Or is illiteracy happening randomly throughout China? It's probably not a dispersed pattern where, like, every 3 counties or provinces, counties divided into provinces. Every 3 provinces have a higher value, or some other pattern where it was regularly and evenly dispersed. Local measures are a value calculated for each observational unit that compare them to their neighbors. And you do have to worry a little bit about edge effects with local neighbors, with local observations, but you just have to be aware of it, okay? So you get an output for each, with local measures, you get one output for the whole thing, one number that says that characterizes the spatial autocorrelation, okay? With local measures, you get a different number for each of the provinces that describes the autocorrelation that exists for it and its neighbors. So your book talks about this Moran's I. And Moran's I is an index of spatial autocorrelation. Here's the formula. Your book does go over a little bit more what each of these terms means. But if you look up at this term right here, you can see that this is a covariation term, because there's a weight, and then there's also a y for a particular variable and a y, another y. So, basically here, it's the y that you're concerned with and the neighboring y's. And it's a ratio of just all of the weights. So the net result of this equation is that if the data are positively autocorrelated, then you'll have a positive value. And what that means is that positive autocorrelation means that it's dispersed, negative or inverse autocorrelation means they're clustered. And random patterns result in near 0 values. So you can look at the number, the output of the number, and see whether or not there's a significant amount of clustering, whether or not there's a significant value of dispersion, or whether or not that pattern in that whatever you're looking at, in this case Chinese illiteracy, is random. In other words, there's no real relationship associated with those values. Sometimes, not in your book, but in lots of other places, these indicators as a whole are referred to as local indicators of spatial association. So you might see the word Lisa applied to that. Okay. Lisa is usually considered using Moran's eye, and then there's a few alternatives, Gary and Geddes or G statistic. And these are all in ArcGIS in the toolbox. So Moran's eye is the most commonly used. Sometimes it's called Ansel and Lisa. The book refers to it as Moran's eye though. So for local indicators, I think I've covered this one pretty well. For local indicators, the statistics is calculated for each aerial unit of the data. So here is the raw data showing literacy. We'll look at some county data for the United States. We've got raw data showing literacy. Here it is symbolized just in different matter by like Z-scores. And then here we see the output of the Moran's eye statistic. You can see in the red areas, those red areas are characterized by having a high value, a high degree of illiteracy, basically, and then neighbors that are all high as well. Not all in this case. This one's not high, but it's a cluster. In other words, it's high, and most of its neighbors have, on average, a high value. This one, same. Most of its neighbors have a higher value. The blue values are low. In other words, there was a low value, and most of its neighbors were also low. And then the white values are not significant. In other words, there's no pattern. It's random in those areas. It's close to random in those areas. The light blue here means that it was a low value and its neighbors were high. It's low, its neighbors. And how do you define a neighbor? There's a few different ways to do that. In ArcGIS, you can set it as a distance. You can set it as ones that are actually touching. This one I must have used a distance because that's not anything. It's not touching anything. Now there's no pink, the high-low. In other words, there's no areas where there was a high value surrounded by low values that was significant for this particular observation. But you might see that in data that you utilize. Okay. Watch out for edge effects. That's what I said there. Okay. So inside of ArcGIS, it's basically looking at this map. It's looking at the this is a particular province here. Okay. This province. Should have highlighted that one because it's going to have to. But these are all the neighbors and whether or not they have a value that's high or not. So here's the sum of all the neighbors. And so each row in this neighborhood matrix describes the neighborhood for that location. Now, ArcGIS will allow you to describe the neighborhood in slightly different ways. That will have an influence on the output. Skip that one for now. This is all calculating the Lisa. I think we'll just do this together in the lab. Okay. Let's go to this slide right here. Okay, so here's the scatter plot of the literacy and the output of the Lisa values. You can see where they fit on this. This plot shows whether or not they have a high positive or a low high negative, a high low or a low low. In other words, the nature of their cluster. All right, so this is a good slide to reference when you're trying to interpret the output of Moran's eye. So if you're in the upper right or the lower left quadrant, the data is indicating that it's similar to its neighbors. If you're in the upper right quadrant, it's indicating that you have values that are similar to your neighbors and they're all high. If you're in the lower left quadrant, you have similar values to your neighbors and they're all low. And then in the opposite quadrants, you have a low value, but your neighbors all have high values. You have a high value, but your neighbors all have low values. So if you were looking at income, you might see something similar. In fact, I've got this. This is an income for city Dallas-Fort Worth area. Okay. This is two different realizations of the same data here. Okay. So this is just showing the values as they cut off on the high and the low. You can see clusters of low. In other words, low income surrounded by low income, high income surrounded by high income. And then you see this light blue area. This indicates a census tract where you've got a low income area surrounded by all high income areas. So you're reading the opposite of one of these. This is a high income area surrounded mostly by low income areas. So they pop out on the map, whereas this is just looking at income in general. You can see the same sort of patterns when you look at this data. But now you have a statistic that shows you how significant and also helps draw out those patterns a little bit better.
Yeah. Moran eyes are 0.59 now. Is that a 59% correlation?
No.
Or what's the interpretation of that?
So Moran's I on that range from 0 to from -1, meaning it's clustered, up to dispersed. So it's indicating that it's that's actually a little bit more on the dispersed side of that equation. From negative meaning it's clustered, up to 1 meaning it's dispersed.
So it's moderately clustered.
Mildly dispersed. So it's on the dispersed. It's on the dispersed side, the positive side. So here's the same thing, medium income, but for some Ohio counties. Basically, you get a value